Hello, my name is Jesus Rodriguez. I'm the Capstone 2 lead for the Analyzing Biological Networks group for the fall 2022 semester. And today I'd like to make a video demonstrating some of the shortcomings we had within the development of the project. To kind of start off, I would like to say for the most part, there were two main shortcomings that I'd like to go over. But before that, I kind of want to make it or demonstrate more of a wish list item. Um, and so we have InfoMap, which is the algorithm that was tasked for us to complete for the semester, mostly done, and basically fully done into the back end. Like the map equation and everything needed for that is ready to be used freely, and we have it fully functioning. There are three other algorithms, and if I remember correctly, they went by the name Spin Glass, multi-level, and fluid communities. Those were the three communities we needed to add, or that are the three remaining communities, I think is better to say. And so, with that being said, even with InfoMap fully being implemented into the backend, there's still some things that we would like to include and then have future Capstone 2 and Capstone 1 students include in their projects when they can. And the first one would be the obvious one, to move this into the front end. Now, there's a reason we haven't done this yet, and that's because there's still some developments that need to be done to the info map before we feel confident that it should be moved to the front end. And what I mean by that is that even though I'm saying that the map equation, the info map is all done, that's technically true. However, the way we're doing it right now is that we are using Luvian to detect our communities, and with those communities that are detected, if you were to run the code for any given test graph, we would see that Luvian partitions the communities into 1, 2, 3, 4 different communities. So Luvian determined that the best partitioning using modularity for Luvian would be 4 different communities. And that's kind of like the basis of what we're using for our map equation and info map algorithm. Since the map equation, or the info map algorithm, is trying to minimize a cost function, we don't really believe that it's doing any of the algorithm is not supposed to split apart the communities on its own. It's supposed to kind of be an optimization of other community detection algorithms by minimizing the cost function. So for example, if we were to take Gervin-Newman for example, and we would optimize that in order to get the shortest or the smallest per step description length that the random walker took throughout the graph. So to really quickly put it, how we have it is that we have Luvian just putting out the maximum or the best possible outcome using modularity to determine the communities, and we're just running the map equation and the info map on that to determine what the average or the per step bit length or the per step description length, I think is better to put it, would be if we ran it there. However, the way we would like to do it is to have it so that we can modify one of the easier algorithms, I guess you could say. So something like Gervin-Newman, which is a bit much more understandable, to be modified and use that modification to partition the communities into, say you have a graph of 25 nodes, we would like to have it so that Gervin-Newman will partition the graph 25 times, and it'll do that for the first time it's partitioning, it doesn't do any partitioning. It'll just treat the graph as an entire module. The second time it'll kind of split the graph in half, maybe, or maybe it'll have its own little community here and another community there, so 2 different modules. The third time there's 3 modules, fourth time 4 modules, all the way up to 25 different modules. And we'd like to run the map equation on each and every single one of those iterations to find out which one would result in the best or the smallest per step description length. And since that was something that was kind of unfeasible to get done with the time we had, considering all the other stuff that we need to get done beforehand, I think it'd be best if we can have future groups to work on that, get that done, and then worry about implementing it the info map algorithm into the front end of the SciFinder plugin, um, depending on how they feel about whether it's ready or not to be pushed into the front end, or if it still needs some time. That'll be up for them to decide. So the second shortcoming that I'd like to briefly go over is actually related to a lot of the Huffman coding that was done. And so we can see that while I said there were 4 different communities, and there are, and we gave them each their own different Huffman codes, that's only one of the steps in order to kind of paint the full picture of the Huffman coding process for the random walker traversing the graph a certain amount of times. And so I quickly like to pull up a picture right here. And basically what this is if you could see on the bottom, it'll show in different colors representing the different modules that are being traversed, the description length of the graph for at which the random walker took a random path. That's the description length for it using 4 different modules. And so you can see the first Huffman coding we can see at the beginning is 111, and that's meant to represent the entrance Huffman coding for entering the red module. So we can see we're starting in the red module, so it starts with 111, and then it moves on to 0000 is the node over here. Then 111 is the node right in the middle over here. Then 01 is the node right over here. And it's kind of traversing through the red module until it kind of gets to a point where it doesn't. And then you'll see at the very end this red one, or this red Huffman coding, is 0001, which is the exit Huffman coding of the red module. And then right after you'll see a 0, which is the entrance Huffman coding for the orange module. And you can see 110 is the first node that entered in the orange community. So what we have done is all of the Huffman codes, the unique Huffman codes per module. What we do not have done is the Huffman coding for the entrance and the exit, the entrance probabilities or the exit probabilities. And so that's something we'd like to include to ultimately have it so that we can have something like this description print out into either the console or the front end, depending on which group works on it, and what they're able to do. But we would like to have it so that the random walker takes a random path and it'll show the description length that it took throughout the graph. And that would be something that if we can add in future groups would be amazing. Because again, we have each of the Huffman codings for the unique nodes, or the unique Huffman codings for each of the nodes within a module. We just don't have it set up in such a way that we can have the entrance and exit probabilities encoded into Huffman codes in order for that to be used as the indicators for whether a module was entered or a module was exited, and to have it all print out and showing the description length as a whole at the very end of it. So that's basically what we would like to include. And as far as those 2 things go, that would be the main 2 concerns we have, our 2 main shortcomings. And so it would be very great if the next group working on this and taking up the torch for this project would be able to incorporate this as efficiently as possible within their semester. But yeah, that'll be all for this video. And yeah, take care, guys.